let's go over the aldol reaction mechanism. This example is one of the simplest aldehydes, and it's easiest to see what's going on. Okay. All right, so here's our alpha carbon. It all gets started by making the enolate using base. Now remember, only some of the molecules undergo this deprotonation. It's not a particularly favorable one. Right, so we take off the alpha proton, and that leaves a minus on the alpha carbon. That's one resonance contributor of the enolate. That's nucleophilic. And so if there's something that's electrophilic around, like another molecule of aldehyde, the carbonyl carbon of the second molecule is electrophilic. And so here's where we can join the enolate alpha carbon to the carbonyl carbon of that second molecule of aldehyde. So alpha is joining to carbonyl carbon in this key part of the mechanism. So let's come over here and draw a nice new line of structure. Here's my enolate part, everything from the original molecule of aldehyde. It's alpha carbon, and now it has joined to the carbonyl carbon of the second one, which had an H and a methyl, and it pushed out onto O, like so. And to finish out the mechanism, that alkoxide formed just grabs a proton. So we grab a proton off water, and that forms the aldol reaction product. So I'm just going to put in all the atoms that we have been putting in so far, and we regenerate hydroxide. So here's our alpha carbon of the part that acted as the enolate, carbonyl carbon of the second molecule of aldehyde. In the Greek letters, we go alpha, then we go beta. So the box carbon is a beta carbon in this product. The aldol product is called a beta hydroxycarbonyl compound. It contains 2 units of the original aldehyde. The one I just put in dashed made the enolate, and the one that I'm circling now and just full circle, this acted as, let's call that the carbonyl acceptor part, if you will.